Let's think about how coordinate descent, gradient descent, and Newton's method all compare to each other. Remember, coordinate descent was, I'm going to just change the x1 variable for a while until I'm happy with that. Then I'm going to change the x2 variable for a while until I'm happy with that. And then if you have an x3 variable and x4 variable, you just go through the variables. And then once you're done with all of them, then you go back and do x1 again, and then you do x2 again, etc. So let's think about what coordinate descent will do for this objective function starting at this current point. So maybe sketch down this objective function and draw what coordinate descent will do. Pause the video while you do that. Okay, so let's take a look. So since it starts here, the minimum left to right would actually be kind of between where this kind of grid line crosses the contour here and where it crosses again over here. So it would actually be going away from the minimum. The minimum should be here to begin with. That's optimizing just with x1, and then optimizing with x2, it should end up kind of roughly halfway between this this part of the contour and that part of the contour, the orange contour. And then once we get there, it should end up kind of roughly halfway between this edge of the contour and that edge of the contour along that horizontal line. And then going this way, it should end up kind of roughly halfway between this edge of the contour and that edge of the contour, or you could say this edge of the green contour and this edge, and then halfway between those. So it's going to be zigzagging like this. So that's coordinate descent. What would steepest descent do? Well, we've seen it would go kind of like this. Its search direction would be like this, and then it would get to about here and then kind of go back that way. So it would zigzag too, which would be a little bit more efficient. So we can say it this way: the tilt of the contours makes coordinate descent zigzag, and it gets worse the more squished those contours are. Gradient descent is okay with the tilt. The gradient kind of tells it which way things are tilted, but it's not enough to kind of unsquish them. If we were operating just on a circle, gradient descent would always point directly toward the center of the circle. So gradient descent is okay with the tilt, but the squashedness makes it zigzag. Newton's method says the gradient is kind of telling me about the tilt, and the Hessian is telling me how squashed things are. And then you could say that it's kind of using the Hessian to unsquish the contours, because in some sense Q is what's squishing the contours. And so when we use Q inverse, that's kind of like remapping space ahead of us to make all the squished contours look more like circular contours. So that's kind of the progression of coordinate descent, gradient descent, and Newton's method, sensing what's going on with the objective function and adapting to the tilt and the squishedness in various ways.